Okay, so we're going to pick up where we left off last class. So we have some problems here. We have the Earth rotating at a constant angular velocity, and given the Earth's radius, we want to figure out what the tangential velocity is that is experienced at the surface of the equator. So we are going to have to convert to miles per hour, and we have the conversion given right there. So step one, we are going to be looking at how are we going to find tangential velocity. Well, right over here we have that v is equal to r omega. So let's switch over to the pen. We have that v is equal to r omega. Our r is going to be 6.38 times 10 to the 6th, and that is in meters. And we are going to multiply that by our omega, which is 7.27 times 10 to the negative 5th. That is going to give us somewhere around 463.8, and that's going to be in meters per second once we put that in the random number generator. Now, we have a conversion, so let's look at this. We have 463.8 meters per second. We know that every 1 meter per second is the equivalent of about 2.24 miles per hour. So we can go over here, let me grab another color. The meters per second are going to cancel, and that's going to give us about 1,039 miles per hour. So it's going pretty fast. Now, if we want to determine the tangential acceleration, so there's the tangential acceleration, so A equals R alpha, and the radial acceleration, so that's the acceleration is going to equal R omega squared. So let's start with the beginning. We said here that the angular velocity is constant. So that means if the angular velocity is constant, then alpha is 0. So that means the tangential acceleration, which is r alpha, is 0. If we look at the radial acceleration, that is going to be r omega squared. So we're going to take that 6.38 times 10 to the 6th, and we are going to multiply that by 7.27 times 10 to the negative 5th, and that is going to be squared. If we put that in the random number generator, we are going to get 0.0336, and we'd be looking at meters per second squared. So then we say, okay, what percentage of your North Pole weight would be lost at the equator due to this effect? So what are we looking at? Well, we're looking at, instead of G being 9.8, our G is going to be 9.8 minus that 0.0336. So that's going to be about 9.77 meters per second squared. If we look at that change, we get that 0.0336 divided by 9.8 times 100. So this would be kind of our new g at the equator. So the difference between the two divided by the original times 100%. So that's going to be about 0.3% less than at the North Pole. So that is what we are looking at. So let's look at problem 8. Problem 8, we have a wheel that is given an initial angular velocity. And because it has some worn bearings, there's going to be a net torque, and that's going to cause it to slow down. We want to know how long does it take before it comes to rest. So we have an initial velocity, we have an acceleration, we know it's going to come to rest, that tells us the final velocity. So what would I do for linear motion? Well, I would use v equals v naught plus at. So here we're going to use omega equals omega naught plus alpha t. 0, 8 minus 0.25 t. So that means negative 8 equals negative 1/4 t. So my time is going to be 32 seconds. Then we want to know how many rotations or how far is it going to go during this time. Now there's two ways I can do this. I can do this version, or I could do omega squared equals omega naught squared plus 2 alpha change in theta. I tend to go with this one because time, I calculated it, I could have an error. Try not to introduce errors. So I'm going to have 64 minus 1/2 delta theta. That is equal to 0. So I get 128 radians. So what I need to remember is if I have 128 radians, one rotation is 2 pi radians. So yes, we're going to go over here, change colors. The radians are going to cancel, and that's going to give me about 20.4 rotations. So I'm going to challenge you to go ahead and look at this tangential and radial acceleration. Remember, the tangential is going to be r alpha. The radial is going to be r omega squared. So pause this, calculate those, and come back.